I guess they're still queuing it up. So today I wanted to talk to you, as soon as the slides come up, there we go, about the particle radiation environment at the moon, and then use that information we've learned from many years now of flight measurements with the crater instrument on the Lunar Reconnaissance Orbiter, and then extrapolate their effects that we're seeing at the moon to other exploration destinations, particularly those that are small airless bodies. I'd like to particularly point out Andrew Jordan, who just moments ago in the other room was giving a presentation on a really remarkable, I think, set of observations that are motivating a new method by which the lunar regolith can be modified by energetic particles, and I'll talk about that, and Colin Joyce, both of whom contributed significantly to this work. So again, what I'd say, a brief summary of what we've learned from the moon, both in terms of the environment there, the particle radiation environment, and the effects. How do we then take that information and scale that environment to other exploration destinations? And I'll look at both galactic cosmic rays and solar energetic particle events. And then, of course, when you go to other destinations, you have to look at other properties of that body, because in some cases that controls the process that's of interest. In particular, I'll look at temperature. And then, even though I won't quite get to it at the end, by the end of this talk, it's still a work in progress. What I really aim to do ultimately is to then estimate the relative importance of these effects at the other bodies. So this is a picture of the crater instrument on the left there. It was launched in June 2009. It looks, it's mounted on the, has the hood ornament on LRO here, and is measuring the passage of energetic charged particles through it, and determining what's called, its primary exploration goal was to measure what's called the linear energy transfer. And this is sort of the baby picture that only a parent could love. This is the really the end product, our goal for the LRO mission in its first incarnation as an exploration mission, because this spectrum here is the thing that determines the radiation environment, which all engineers use to estimate the impact on both humans and robotic systems. So this is sort of the culmination that shows the galactic cosmic rays as they pass through the instrument. We see a series of peaks here, each one of those mapping to an ion species that's caused and accelerated in the galaxy through supernova acceleration from shocks and so forth. And so it's this spectrum that was our primary goal for the initial part of the mission, from which you can then calculate practical applications for the environment and the effects on humans. And so this is a pie chart and a bar chart, a breakout that shows the dose and dose rate estimates from galactic cosmic rays after they've passed through the cosmic ray telescope, which includes slugs of tissue equivalent plastic that produce then internal to the instrument a radiation field that will be similar to radiation passing through an astronaut's body. The volume of that is about the thickness of your torso. And so you can see in this that we have contributions from protons and galactic cosmic ray alphas, then heavy ions. Then there's this albedo coming back from the surface, both in the form of neutrons, protons, and a whole alphabet soup of nuclear byproducts. So we've looked not only at galactic cosmic rays and their effect, but also the impact of solar protons, and this is some work that Nathan Schwedron did, comparing some models of our expectation of the arrival of solar protons from events near the sun and the resultant radiation field near the moon. This is a plot that shows how we use both galactic cosmic rays and, in principle, solar protons, but in this case just GCR, to look at the secondary byproducts coming off the moon. And the top figure here is an early figure from Jody Wilson, and he had a poster the other night looking at the map of proton albedo, and of course the one that you've seen below that Gordon Shin talked about and Tim did earlier this week from the LEN team. So again, using these energetic particles that are part of the environment then as a way to do some science by looking at the effects on the surface. Very powerful tool. Another aspect that we've looked at is chemical weathering from both galactic cosmic rays and solar energetic particles. This was some work that Nathan Schwadron initially did, and then a very comprehensive and nice paper by Andrew Jordan a year later. And the recognition was that the penetration of these galactic cosmic rays and solar protons in particularly permanently shadowed regions can disassociate molecules in water ice to form H2. And so this work, I believe, showed that there was a nice consistency with the measurements made by LCROSS during the impact as measured by the Lyman alpha instrument on LRO, consistent with the kinds of fluxes of GCR that we've seen in terms, and solar protons over the course of the history of the moon as a function of the gardening depth with a very good synergy with the measurements made from the LCROSS impact. For the rest of the talk, I'd like to focus on the solar energetic particle aspects, and this is what I was talking about. Andrew Jordan had just given the talk next door, and that's the production of deep dielectric discharges. So the idea is that during a solar proton event, these particles can penetrate down into the regolith, and they do so in a differential fashion as a function of energy, and so you build up essentially a capacitor. And as we've heard earlier from Bill Farrell's talk and others, the moon is a pretty poor conductor, and so you can build up electric fields, and eventually that charging dissipates as in a capacitor, and it does so depending on how fast you're charging. And so if you charge it very, very fast on a time scale that's short compared to its discharge time, then you basically get electrostatic discharge. You get little lightning bolts basically inside the moon, and there's a property here that the lower the conductivity, the more the charging. And so in the case of lowering conductivity, you want to have very cold regolith, and you do that in permanently shadowed regions very nicely. This is a movie of a laboratory demonstration of this process. It's a slug of plastic, very low conductivity, and this brave gentleman is applying a very large electrostatic potential, charging it up very quickly, faster than its discharge time, and you get these characteristic patterns. And we believe this is what's happening in permanently shadowed regions during very large solar proton events. This is a figure that shows the lifetime of the LRO mission, and on the vertical axis is the fluence of the particles that would lead to this discharging phenomena. And here's the breakdown threshold. In the lifetime of the mission, we believe there were 2 events during which probably breakdown was occurring in the permanently shadowed regions. And we believe then, just in the lifetime of the LRO mission alone, just 4 or 5 years at the time of this figure, maybe up to 8% of the permanently shadowed regolith grains in the top first millimeter received a breakdown channel. And these can be very disruptive, powerful events that modify the properties of the regolith, and Andrew talked about that. Here's a map now showing over the course of the time after which regolith had been gardened at both the North and the South Pole, showing the number of events in color, and the color scale here is 10 to the 6 events, ranging from 0 to 2.5. So these are occurring very frequently over geologic timescales, in this case associated with the time during which the regolith had been gardened and exposed. So we'd like to now, just in the last minute or two, I'd like to scale how the GCR varies through the solar system. And basically, the interplanetary magnetic field acts like a shield to the incoming galactic cosmic rays. That sets up essentially a radial gradient of GCR intensity, highest near the outer parts of the heliosphere, lowest near the sun, but not a huge difference in terms of the overall intensity. It's important for understanding GCR transport, but for this application, it's a relatively weak variation. It also varies with time over a solar cycle, about by a factor of 2 every 11 years. And so there's a relatively, you'd say, modest variation maybe between the inner parts of the solar system and the outer parts. Nevertheless, it's important throughout the solar system then, as it is at the moon, for other bodies like Mercury, Phobos, Deimos, and Pluto, and for all the things we talked about, radiation effects and doses, and also for albedo off these objects. And so we would expect to be able to do the same kind of remote sensing at these objects as we do at the moon. The solar proton intensity is a bit different. And so these solar particles are generated near the sun during explosive releases of magnetic energy, and these are association with shocks with coronal mass ejections. These solar protons moving near the speed of light propagate away from the sun. They're constrained by the magnetic fields they're tied to, but they ultimately filled vast parts of the solar system. So we've used a model called EPREM that Nathan Schwadron has developed to estimate how solar particle intensity varies as a function of distance from the sun out to Jupiter. Then we scaled it geometrically thereafter. This shows a particular event that occurred in March of 2012. That was one of the two big ones. That shows the flux of particles at 27 mega electron volts, these are protons, as a function of the day of year in 2012, then as a function of distance. So the red curve here is at 1 AU, and as it moves successively further out, it arrives later in time and starts to become smeared out as it moves out through the solar system, filling a greater volume. That's flux. We can also look at fluence as a function now of heliocentric distance. So fluence is just the time integral of that curve as a function of position out, now as a function of energy. And so we can use these results now to estimate how things look throughout the heliosphere. So let me do this, and this is where we have to bring in temperature. So this is a figure that shows the time scale of the electrostatic breakdown time as a function of regolith temperature. So if you look at permanently shadowed regions of the moon, it's about 12 days. So the charging events are short compared to that 12 days. So that's an important property here. We can then start looking at these other objects. We can look at permanently shadowed regions of Mercury, where the time scale is about 4 days. It's warmer at Phobos Deimos, and that time scale is about a day. That's starting to get near the edge of the importance of the shortness relative to the solar proton event. And at Pluto, out here, again, straddles the temperatures of moon, depending on the season, but roughly 10 to 15 days or so. We can then look at the electrostatic breakdown rate, and this has been estimated by looking at particular events. So this is the breakdown rate an event per year, again as a function of the regolith temperature. Here's the moon in the permanently shadowed region. So we have about 1.5 events per year. We can then look at Mercury, where because Mercury is closer to the sun than the moon, we have a higher fluence of particles. They're more focused, and so the rate is a little bit better. Even though it's a little bit warmer overall than the moon, we have still maybe even greater, about twice the rate expectation at Mercury than the moon. If we look at Phobos and Deimos, it's warmer yet, and so the rate is down quite a bit. And it's also further from the sun, so the fluence is down. So that net together, it's quite a bit lower expectation at Phobos and Deimos. And here we are, way out at Pluto, where it's very cold, and so that helps. The regolith is nice and prepared to be charged up, but because it's so far from the sun, the fluence is quite a bit lower, and so the rates may be more like 10 to the minus 3 per year, which is actually pretty comparable to the Phobos and Deimos thing here. So you can see that the trade space between temperature and distance from the sun, despite those differences, they're more alike than maybe different. Okay, let me summarize. My time is up, and just comment that ionizing radiation throughout the heliosphere has both that intrinsic science value, I think of those as the truths, and also very important exploration applications. And those are the consequences that have both a practical consequence for radiation for astronauts and also really interesting, I think, science issues about how these bodies might be modified by the radiation. And I would say a really nice, interesting surprise and outcome of the study is how solar particle events are probably producing these little lightning storms on the moon during solar proton events. And we'd expect that same process at different levels to be occurring at these other airless bodies throughout the solar system, probably pretty important at Mercury and maybe even at Phobos and Deimos, maybe less likely in the outer solar system, but I would say still a work in progress, and so stay tuned, there's more to come. And I think we'll leave it at there and take questions if there are some.
I think we'll be transitioning to closing words in a few minutes, but if anyone wants to chat with Harlan.
Derek Sears, NASA Ames. Is this on?
Yes.
You can see the effects of SEP interactions with the lunar regolith in the Apollo samples. Is there anything to be gained in comparing your thoughts and ideas with what we see in the Apollo samples?
It's a great question. I'm sure the answer is yes, and so we should talk after.